Hi, everybody. So here's where the survey ended up. It was really, really close. So with 26 of you voting, 12 no's and 14 yeses. What it means is I will finish off the electricity unit, but I will modify it. I will shorten it a bit. We'll get through Kirchhoff's rules and basic electric circuits, and that's as far as we'll take it. So I'll truncate it a little bit, but make sure we sort of wrap it up with all the big ideas. And one of the big ideas today is Kirchhoff's rules. Kirchhoff was Prussian. He was the one who analyzed electrical circuits in a mathematical way, and we'll get into those today. But let me cruise into this real quick. Take a look at this. This is an old problem. The question is what's the current through and the voltage across the bottom 2 ohm resistor when the switch is open and closed? And this goes back to the idea of resistor networks. So first of all, quick note on this. What does it mean when the switch is open? It means that this switch is not connected. There's an air gap between these two ends, which means we assume that air is a really good insulator unless you've got crazy pressure where it can jump across. In this case, not crazy pressure, not crazy electric potential. What does that mean? It means no current at all can flow through this part of the circuit. So then what do we have now? Well, we have this 2 ohm resistor in series with this 2 ohm resistor down below. What does that mean the total resistance of the circuit is? Well, if you remember, for resistors in series, you just add them together. So 2 plus 2, total resistance is 4 ohms. I was thinking next part. What's the current out of the battery in amps? Just using Ohm's law, current equals voltage over resistance. 12 volts over 4 ohms, that means that 3 amps is leaving our battery. Now, where does that 3 amps go? Well, remember, it can't go, when it gets to this junction right here, it can't go up this direction because there's no path for it to take, which means it's all going to go through this 2 ohm resistor down here, and then back over here it's going to recombine. Nothing comes from this side, all 3 amps there. And we got 3 amps then flowing down through this resistor here. And I guess I could draw 3 amps going over here too. So that tells us what the current is through that. How do we calculate the voltage across it? Well, when they're talking about the voltage across it, they're talking about the voltage drop or the potential change across it. And if you remember, there's a couple ways of solving it. One way would be to take a look at the voltage drops here. The voltage drop here, current times resistance, 3 amps times 2 ohms, gives us 6 volts, which means there's 6 volts here. And if you work it out real quick, there'd be 6 volts here. The voltage drop across this resistor, because I go from 12 volts to 6 volts, has to be 6 volts. Oh yeah, that makes sense because sure enough, current times resistance is equal to 6 volts. It all makes sense. Oh, I put it in there. What happens now if the switch is closed? So now the switch is closed means it makes an electrical connection here. What does that mean? Well, remember that these two resistors are in parallel, side by side. How do you figure out the resistance of 2 resistors in parallel? It's just 1 over the total equals 1 over the first resistance plus 1 over the second resistance, plus any additional resistances you have. And so if you solve that, you'll discover that this whole thing is equal to 1 ohm. So this whole thing, which is 1 ohm, is in series with this 2 ohm resistor down here. What's the overall resistance of this whole entire circuit? It's 3 ohms. What's the current? Just using Ohm's law, 12 volts over 3 ohms equals 4 amps, which means 4 amps go out of the battery. And then over here, the 4 amps comes in, and part of it goes this way, and part of it goes this way. And then over on this side, it recombines, so the 2 parts recombine into a single current. This makes it a little bit more challenging because we don't know exactly then what are the currents for either one of these 2 resistors. But what we can do is we know all of the currents got to go back through this resistor down here, all 4 amps of it. That's only one path going back to the battery. And again, remember, current is never used up in a circuit. It's just the potential that's used up, the voltage. So solving this in terms of potential, we know we're up to 12 volts here because we've gone for a 12-volt battery. And the voltage drop for this resistor down at the bottom is 8 volts, which means If we're at 0 volts here, we must have been at 8 volts here. And now we can actually do a little bit of math magics. What's the voltage drop across these resistors? If you go from 12 volts and go through this resistor, you end up at 8 volts here. Or if you start at 12 volts and go through this resistor, you end up at 8 volts here, which means the voltage drop through both of these resistors must be 4 volts. No matter which path you take, you're going to lose 4 volts by the time you get to this point. Once we know that, you can very quickly calculate the currents. Why? Because we know the voltage drop is equal to I times R. In this case, the resistance is 2. The current must be 2, so that the voltage drop is 4. And that's true also for this resistor up here. And so you get some fun parts. Here's how this would look like in an AP question. And you're saying, oh, I know that they're not going to offer any multiple choice questions, but they could still ask you this kind of, oh, actually, they won't ask you an electricity question now. Sorry, we just know that. But take a look at this one anyway, just to sort of wrap it up. Potential difference across the battery is 3 volts. How much will the magnitude of the potential across R2 change when R3 is removed and the branch left open? Well, first of all, let's take a look at the first circuit here, and let me move my pen out of the way. Total resistance, remember these two resistors in parallel would be 1 over 100 plus 1 over 100, or 2 over 100 equals 1 over R. And you can sort of see that these are 50 ohms. That's in series with this 100, so the total resistance is 150. The current in the circuit, 3 volts over that, is 0.2 amps, which means we know we've got 0.2 amps leaving the battery and 0.2 amps going for that resistor. And very quickly then you can figure out the voltage drop is 2 volts across that resistor. Solving the potential real quick here, we know we'd be at 3 volts right here, as well as here we haven't any voltage drops there. But when we lose the 2 volts here, we're down to 1 volt. And yeah, this end over here is back at 0 volts, either there or there. So what's the voltage drop across this resistor? The answer is the voltage drop, oh, I put in that, it must be 1 volt across either one of those resistors. So now what happens if we take out R3? Well, if we take out R3, we get, oops, I'm going the wrong way. No wonder it's disappearing. We take out R3, we get this circuit. Again, this is like air down, or just an air gap. There's no current flowing through here. The voltages aren't great enough for it to zap across that. How do we solve it? Well, total resistance now is just 200 ohms, 100 plus 100, just in series. The current is going to be that, and all that current's going to flow through there. We can very quickly figure out the voltage drop through R1. And doing our potential differences here, we know we're going to be at 3 volts again here. If we lose 1.5 volts, we're going to be at 1.5 volts there. We know at 0 volts there, which means the voltage drop here now has to be 1.5. And yes, we could also work it out from the current here. We also know the current through this has to be 0.015 amps. Times that, we could have figured out the voltage drop that way as well from the beginning. So what happens to the magnitude of the voltage across R2? It increases by a factor of 0.5 volts. All right. Multi-loop circuits. This is where Kirchhoff comes into play. And don't panic. Multi-loop circuits are where you've got multiple batteries in multiple loops of the circuit where you can't simplify it. You've already done multi-loops with just plain resistors where you just have one battery. But if you've got multiple batteries, you've got to use a little bit more fancy math. And Kirchhoff, as I mentioned before, here's how his name's spelled, has a couple of rules. The junction rule. The sum of the currents directed into any junction equals the sum of the currents directed out of the junction. So for example, here's a junction. A junction is just where wires converge. So say for example, I had 2 amps going in this way, 3 amps going out this way, and 5 amps going in this way. Could you please tell me what the current is through this wire? And you might say, whoa, 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 how am I supposed to figure that out? Well, there's the bell. Well, if you look at this, you have a total of 7 amps flowing into this junction. You've got 3 amps flowing out that way. Because current is never stored at the circuit and never created or destroyed, you can very quickly figure out that this branch of the circuit must have 4 amps going out. Total of 7 amps going in, total of 7 amps going out. The loop rule, around any closed loop circuit, the sum of the potential rises or drops equals the sum of the potential rises. You've seen this before. As we work around the loop, the battery gives it potential, and as you work through the resistors, you have voltage drops. And you know the sum of the increases plus the sum of the decreases always adds up to 0. It's a pretty simple idea. And you're like, oh, Kirchhoff's rule is super simple. Yeah. It looks so simple. But then there's my favorite thing. I call it the rules for applying Kirchhoff's rules. You're like, what? Yeah, I made these up. Guess the direction of the current for each resistor. You're like, really? Yeah, guess. What happens if you guess wrong on this? Don't worry. If you guess the wrong direction, you'll just get a negative answer. And it means, oops, it's the other direction. Label the current for each resistor. And use the junction rule to limit the number of unknown currents in the circuit, just so you don't have to write lots of equations. Choose your loops and choose the direction you wish to work around each loop. I'll explain that in a second. Write your equations for the loop using the loop rule. If you go for a resistor in the direction of your guess current, the voltage drop is IR. If you go for a resistor in the opposite direction of your guess current, the voltage drop is negative IR. Okay. And if you go for the battery in the direction of conventional current, the voltage added is the EMF. That's supposed to be the voltage. If you go for a battery in the opposite direction of conventional current, the voltage added is negative EMF, or negative voltage. All right. You're like, what do these rules mean? It always helps to actually see it in practice. So here is a multi-loop circuit that has lots of resistors and multiple batteries in it. This is just the way, again, that my circuit draws it. This is a single 12 or 10 volt battery. This is a single 12 volt battery. And the resistors here, because my software draws them this way, are just little boxes instead of the standard little form that we usually use on the AP test. So how do we solve this? First step, we guess the direction of the current. So I'm going to arbitrarily guess that the current through this resistor up here is heading to the right. I might be wrong, but we'll find out. The reason is I got this 12 volt battery trying to push current around this way. Yeah, I got a 10 pushing it this way, but I'm going to guess it's that way. And I'm going to call that current I1. Now, the moment I've labeled this current going this direction, I immediately can label this resistor down here, the current through it. Why? Whatever current goes through this part has to go through this part. So the current going through this 2 ohm resistor has to be the same as this resistor. And if I drew it going this way here, I've got to draw it going this way here. All right. Now, how about over here, this 4 ohm resistor? Well, the current here is not necessarily equal to the current here because I've got a junction right here. Some of you could split up or add in. So I'm going to call this current I2, and I'm going to guess it's going to the right. Again, just an arbitrary guess. If I get it wrong, I'll get a negative answer. And the moment I draw that, I immediately know what the current is through this resistor. It also has to be I2, and it's got to be going this direction. Remember, batteries don't make charge. They just increase the potential. So whatever flow rate is going into the battery comes out of it has to be I2 as well. And then that finally leaves me with this 1 ohm resistor. The current going through this is not I1, it's not I2, and I'm going to guess that it's going upward, so I could call it I3. But remember, one of the rules I suggested is try to limit your number of unknowns. If you look at this junction down here, what you've got is you've got I2 going into it, you've got I1 coming out of it, and I'm saying some current is going up this way. We know that the sum of the currents going in have to equal the sum of the currents going out. What is this current going to have to equal? Well, you can realize that I2 has to equal I1 plus my unknown, I'll call it X. And if you solve for this current right here, you'll discover that you can just rewrite it as I2 minus I1. That's my X down here. What's the advantage here? Now I just have 2 unknown currents in this circuit, and those are what I'm trying to solve for. If I have 3 unknowns, I'm going to have to write 3 simultaneous equations to solve it. And I want to try to avoid that if possible. All right, my next thing I need to do is to choose the direction I want to work through the loops. Now, how many loops are actually here? Well, there's actually 3 loops. Here's a closed loop. That's loop number 1. Here's another closed loop. That's loop number 2. And here's loop number 3. I could just go around the outside of it. But because I only have 2 unknowns, I only need to choose 2 of these 3 loops to be able to solve this. And so I'm just going to choose, this is my loop number 1. I'm going to work around it clockwise. Why? Just because it's convenient, because most of my currents are going clockwise, although this current's going counterclockwise around that loop. And I'm going to choose this as my loop 2, and I'm also going to work around it clockwise. Why? Because all of my currents for my resistors here are clockwise for this one. Makes it pretty nice. All right, so what we have here, and Kirchhoff said, the sum of the voltage drops, which remember is equal to I times R, has to equal the sum of the potential gains, in this case the battery voltages. So what is it for loop number 1 here? Well, I'm going to start with this resistor right here. And so what's the voltage drop through it? Whoops, I'm sorry, I actually started, I forgot when I wrote this. I'm actually going to start down here with this resistor. The voltage drop for this resistor is I times R, which in this case is I1 times 2, but I'm just going to write it as 2I1. Now working around the loop, getting to this one now, that's going to, voltage drop for this one is going to be 1 times I1. And now here's the issue. As I'm working around my loop, as I'm working through this resistor going this direction, my current, I guess, was going upward. So the voltage drop for this would be normally 1 times this current. But because I'm working around the loop clockwise, I'm going backwards against the direction I drew the current, I'm going to actually use negative 1 times the current. Why? Because I'm working backwards against it. It's not going to be positive 1 times that. And then I also have this problem here. I'm going to go through this battery backwards. Positive terminals there. Normally we draw a current going out that way. Because of it, instead of saying my voltage of the battery is 10, I'm going to say it's negative 10 because I worked around it this way. What would have happened if I worked around this loop in the counterclockwise direction? Well, then these two would have become negative. This would be positive, and this would be positive. But it turns out to be equivalent in every way mathematically. All right, loop 2. I'm going to start out, this time I'm going to check beforehand, with this resistor. And this time I'm going through it in this direction. I'm working around the loop this way. And because it's the same direction as drew the current, it's just going to be 1 times the resistance, 1 ohm, times the current, this. Now working through this resistor, this is nice. It's just 4I2. And then down through this resistor, it's just going to be 5 times I2. And because in all these cases I'm working in the direction of my guess current, they're all positive. And now this, I've got 2 batteries. The 12-volt battery I'm working through this way. Oh, that's the same direction I would normally draw a conventional current coming out. And for this one, I'm working around this way. That's the same direction as I draw current coming out, which means my 2 voltages in this case are both positive. And because they're both pushing in the same direction, I just add them together. If you simplify this and plug it into your Inspire, you'll get something like this. So I've got, this first equation becomes 4I1 minus 1I2 equals negative 10. And the second equation becomes 10I2 minus 1I1 equals 22. If you solve that, and I know it's kind of hard to read here, you'll get that the currents are this. And you're like, oh, no, it's the end of the world. We guessed the wrong direction for I1. Actually, I guessed the wrong direction for I1 intentionally. I1 is actually negative 2 amps. What does that mean? It means the current is actually not flowing this way. The current is actually 2 amps going this way. And the same thing's true down here. The current is 2 amps this way. Oops, got my 2. And now what is the current? Oh, these are fine. The current here is 2 amps going this way, 2 amps going this way in the direction we guessed. But how do we solve this current? Is it in the right direction? Well, if you look at it, I2 is 2 minus I1, which is negative 2. The current through this one is 4 amps, and that's positive. It is in the direction that we guessed. So the current here is 4 amps going upward. Okay? So it's not the end of the world if you guess the wrong direction. Oh, how do we choose what direction to work around our loop? We just choose any direction that makes it look like it's going to be more convenient for us. All right, let's try another one now that you've seen this. Oh, just real quick on this, if we say this is 0 volts right here, does it actually work out? Well, if you check it, let's see. Oh, let's work around this way. Current's actually going this way, so by this point we have a voltage drop of 4 volts. We'd be at negative 4 volts here, but then we gain 10 volts here, which means we'd be at 6 volts. The current's going through this. The voltage drop is 4 volts, 4 amps times 1, which means we're at 2 volts here. The voltage drop across this is 2 volts, which puts us back at 0 volts there. Oh yeah, look, that makes sense. And it should work around this way too. Oh, yeah. The voltage drop across this resistor is 10 volts, 5 times 2, and it drops that direction, which means for a negative 4 there, and we drop by 10, I must be at 6 volts here. 6 dropping 10 gives me negative 4. What's the voltage here? And I know it's a little bit ugly to look at. I gain 12 volts, which means I must be at negative 6 volts here. It's negative 6 plus 12 gives me that. And then here, the voltage drop is 4 times that, 8 volts. If I'm at 2 and I drop 8 volts, oh yeah, negative 6. It is all consistently, it all works. It's a good way to check your answer afterwards. All right, example number 2. I'm going to guess the current here is going to the left. I'm going to call that I1 for that resistor, which means this one has to be I1. And over here, I'm going to guess that it's 2 amps going that way, which means that has to be 2 amps over there. What about the 3 ohm resistor? I'm going to guess the current's going up, and I could call it I3. But if you look at this junction real quick down here, what's going on here? I've got I2 coming in this way, and I1 coming in this way, and then this current going upward here. What is this going to have to be? Well, by definition, it's going to have to be equal to I1 plus I2. All the current going into a junction has to equal the current coming out of it. Now solving it, I'm going to choose loop 1 going counterclockwise. Why? Because most of these currents are going counterclockwise, which makes it life easier. And for loop 2, I'm going to say it's going clockwise. Why? Because everything's going clockwise around it. So solving it just in terms of loop 1, starting with this top resistor right here, voltage drop is 2I1 plus 1I1, that's a voltage drop there, plus the voltage drop going through this one, and again I'm going in the direction I drew the guessed current, so just 3 times I1 plus I2 equals the battery voltage in that loop, which is just 12 volts, and because I'm working this direction, the same direction we normally draw a current coming out of it, it's positive 12. You're like, hey, I like this one better. Yeah, it's a little bit nicer. Now how about loop 2? Loop 2, let's start up here, this resistor here. Voltage drop through it would be 4I2, and that's in the direction I'm working around my loop. Plus this one, which is going to be 5I2. And then working through this resistor over here, it's in the direction that I'd guess the current. So that's going to be plus that. Equals the battery voltage in this loop, which is just 6 volts, and that's again in the direction that I'm guessing as I work around the loop, because that's the direction current would come out of it, is 6. Plug it into your Inspire, you'll get that the two currents are 2 amps and 0 amps, which means what's the actual current in this loop? This is 2 amps going this way, this is 2 amps going this way, and there's absolutely no current here. The current is 0, doesn't even have a direction. The current through this one is 0. And the current here is going to be 2 plus 0. It's just going to be 2 amps going up this way. And yeah, I don't know if we should do it again. You could double check it real quick. You could check the voltage drops. I'm going to start here with 0 volts. I end up with 12 volts after I go through the battery. Through here, I lose 6 volts, so I'd be at 6 volts here. Voltage drop through here is 4, so I'm going to be at 2 volts here. Voltage drop there's 2. Yep, sure enough, it works. And now let's take a look over here. What's happening on this side of the circuit? Well, I'm at 12 volts here, And I know that this battery gives me a 6-volt boost going this way, so I must be at 6 volts here. There's no current here, so there's no voltage drop across this resistor. I times R is 0. So that's at 6 volts. There's no voltage drop through this one, so, oh yeah, it is consistent. It's just that absolutely no current actually goes around this part of the loop. This battery is preventing it. All right. And now finally, one last one that I don't have prepared. Let's take a look at this one real quick and guess the direction of the current. I'm going to guess that the current through this one is I1, which means the current through this one is also I1. I'm going to guess the current over here is going downward. I'm going to call that I2 in this other loop. And the current here is I2. And now the current here, I have no idea direction it's going to go. Let's assume it's going upward. I might be wrong on it. And looking at the current here, I've got I2 going into this junction. I got I1 coming out. So what's the current going up here? This should be I2 minus I1. Working on the loops, I'm going to work around this loop right here. That's going to be my loop number 1. And let's go around this way for this one, and this is my loop number 2. And so solving it real quick, the first loop, I'm going to start from the top, gives me 2I1 plus, or actually minus, 2 times I2 minus I1 for this resistor, because I'm working against the direction as I work around clockwise. I drew this going upward, plus this resistor, which is going to be 1 times I1, equals the battery voltage, and I'm going to use positive 12 because I'm working through this direction. That equation can be simplified down to 5I1 plus or minus 2I2 equals 12. All right, so this is loop number 1. And now for loop number 2, let's start at this resistor right here. That's going to give me 2I2 plus 4I2, that's a bottom resistor, plus positive 2I2 minus I1, because I'm going through in the direction I guessed it, equals the battery voltage, which is positive 24, because I'm also working in the direction. Everything's going the right direction. And this bottom equation can be simplified down to negative 2I1 plus 8I2 is equal to 24. So here's my two equations. If you plug that into your Inspire, so checking it, we get I1 equals 4 amps and I2 equals 4 amps. Both positive, which means that these directions were all correct. This is 4 amps going this way, 4 amps going this way, 4 amps going this way, 4 amps going this way. But there is something interesting right here. What's the current through this resistor? Well, we get 4 amps minus 4 amps. There's actually no current at all through this one. The current here is 0. There's no current flowing either way. And let's just double check it real quick. If we make this 0 volts, we get 12 volts here. We lose 8 volts here. So we're down to 4 volts here. We gain 24, so we're at 28 volts here. We lose 8 volts here, so we're back down to 20 volts. Here we lose 16. We're back down to 4 volts. And then here we lose 4 volts, we're back down to 0. And notice that the voltage here and here are both 4. So delta, or the change in voltage across this, is 0. So the current is also 0, even though the resistance is 2, because there's no voltage drop across it. Okay? All right. Here's another quick example. I don't know if we need to do another one. Two identical. I'll skip this one. If you want me to do it, I'll do it later. Here's one of the textbook problems for tonight. Find the equivalent resistance between A and B in this figure. So what do we have here? If you take a look at this, you sort of work from inner to outer. So here's our two endpoints. To start out with, you might notice that these two resistors are in series with each other. And so what's the total resistance of these two pieces? The answer is, just adding those together, 8.6 ohms. Now that, in turn, is in parallel with, and I'm going to change colors here real quick, is in parallel with this 1.8. So now we've got this 1.8 in parallel with this 1.6. What's the total resistance of this one? We got a resistor in parallel, so we go 1 over 1.8 plus this whole thing right here, which is 1 over 8.6. Forgive me for a second, I'm going to grab my Inspire. And 1 divided by 1.8 plus 1 divided by 8.6 gives us that, and the reciprocal of that answer is, all right, so all of this together is 1.49 ohms to 3 sig figs. And now we've actually solved it. Why? If I switch colors one more time. So all of those resistors that I've got enclosed already is just equal to 1.49. So now I just have this in series with this whole thing, in series with this whole thing. So what's the total resistance of this circuit? It's just going to be 2.4 plus 3.6 plus 1.49. I guess you could round that to 1.5. And we get, let's see, that's 6 plus that, 7.49 ohms. And that is our final answer. Or you go 7.5 if you want to go to 2 sig figs, which I guess is what we have here. On your worksheets tonight, you've got a couple of problems like this. In this case, you've got light bulb X in these situations, and you're supposed to rank the brightness of the bulb from greatest to smallest. Well, if you check here real quick, assume these are 1.5 volt batteries, notice you got the positive end connected here, the negative end. So what potential difference is this light bulb going to see? It's going to see a potential difference of 3 volts. All the way from 0 volts here, 1.5 here after one battery, then for a second one, up to 3 volts, and then back down to 0. This one, we've got 2 batteries in parallel. Both of these work together, and it's like pumped side by side. We talked about this before. This light bulb is going to see 1.5 volts, a potential difference, and this light bulb is going to see 1.5 volts, a potential difference. Assuming that these batteries are all capable of supplying as much current as needed, which one's going to be the brightest bulb? The answer is A is going to be the greatest, followed by a tie between B and C, both of which are seeing a potential difference of 1.5 volts. Down here, let's take a look at this as well. We've got 1.5 volts here, 0 volts here, and now here's this strange thing. This wire connects 2 points, which means this point over here is also going to be at 0 volts. So this light bulb is going to see a potential difference of 1.5. No current at all is going to flow through these 2 light bulbs. If it's a choice of going straight through this wire or through these 2 resistances, it's going to go straight through here. You can also try it mathematically. If you have 0 ohms in parallel with any kind of resistance, the overall resistance approaches 0. How about over here, what's going on? In this case, this is 0 volts. This is 1.5 volts on this side. But now take a look at this. This wire connects these 2 points. This point's also going to be at 1.5 volts. So this light bulb is going to see a difference of 1.5. But what's the potential difference across these 2 bulbs? The answer is nothing at all. 0 volt difference across this. This light bulb won't even light. All the current's just going to go through this wire, through this light bulb and back. Just like here, it only goes through this one and back. And then finally over here, what happens? We end up with 1.5 volts here, 0 volts here. Assuming that we have the same current going for each one of these, in this case, what's going to happen? It's going to skip this light bulb here in the middle and go right over to here. And the potential drop across each one of these, assuming they have the same current and the same resistance, is going to have to be half of the 1.5. So the voltage drop across this one is going to be 0.75 volts, and the voltage drop across this one is going to be the same, 0.75 volts. So I'm running out of space. So the brightness of these bulbs, which one's the brightest? In terms of X, this one's completely turned off. This one's getting a full 1.5 volt potential difference, gives a maximum current. So A is going to be the greatest. B is completely off. And C, it's getting half the potential difference, so probably half the current. So it's going to be A is greater than B, which is greater than C. Or sorry, I just messed it up, didn't I? Shoot. Sorry. Is greater than C, this one, which is greater than B, which is the middle one, which is actually turned completely off. We do a little bit more down here as well. This one, you can sort of see what's going to happen here. The current's going to go through this filament and then take this shortcut right back. This one's going to have a potential difference of 0. Same thing's going to happen here. What in the world? Go back through here. And then this one, it's going to go through this one, skip this one because it's got a nice short path of 0 resistance. So what's the answer in this one? They're all 0. There's no current going through any one of these. They're all turned off. And then finally, they've got an amp meter here with 3 light bulbs in series. If each one of these has a resistance of R, the total resistance of the circuit is 3R. Does it matter where you put the amp meter? Does the current change if you measure it here, here, or here in the circuit? The answer is they should all be the same. And you should kind of remember that from the other day when we did some of these. These are some quick multi-loop circuits just with resistor networks. Let's just do one of these for a quick example. So in this case, this is 20 ohms. Oops, my ohm is a little bit bad. R3 is 30 ohms. R2 is 20 ohms. And R4 is 8 ohms. And our battery is 12 volts. So first of all, we have to figure out the total resistance of the circuit. I don't know if you can see it right now, but these two resistors are in parallel with each other. And so we end up with 1 over 30 plus 1 over 20 equals 1 over R. Common denominator, 60. So 2 over 60 plus 3 over 60 gives us 60 over 5, or 12 ohms. So the total here should be just 12 ohms. And that is if you can look at this, we've got 20 ohms in series with this whole mess, in series with this. So the total resistance for this first circuit is 40 ohms. Just 20 plus 12 plus 8. What's going to be the current in the circuit, or the current flowing out of the battery, just V over R, is going to be 12 over 40, or, let's see, reducing it real quick, 3 over 10, 0.3 amps. And you can do the same kind of thing for the other two circuits. Calculate the current through R2. Yeah, we have to figure out potential differences if we want to do that. You could figure out what the potential is at point B and at point C. And then you could figure out the current through this 20 ohm resistor. How would you figure that out? Well, you know the current through this one is 0.3 amps. And the current through this one going this way is 0.3 amps. For example, the voltage drop here would be 6 volts. So we'd be already down to 6 volts here. And here, voltage across this would be 0.3 times 8, 2.4 volts. Assuming that this is the 0 point again, this would be at 2.4 volts. So the difference between these two would be 3.6 volts. So if delta V is 3.6 volts, what are we looking through? The current. The current through this resistor, the 20 ohm resistor here, would just be I equals V over R. Or you could do a bunch of different ways. We know the voltage drop is equal to IR. But just 3.6 over 20. And you end up with 1.8, 0.18 amps is the current through that for R2. It's a lot of just plain math, I'll admit it. There's another one on here. Yay, finally a brain break. The famous trios below have their common letters shown. Can you figure out who, what, and where they are? They're the form of X, X, and X. Here's a quick example. This is the clue, and the answer is reading, writing, and arithmetic, the three basics. All right, so I'm going to show these, and I'll show you the answers. Ooh, man, these are hard. Wow. I'm going to do a countdown from 5, see if you can figure out any of these. I'm actually stumped on a couple of these. 5, 4, 3, 2, 1. Calm, cool, and collected. Signed, sealed, and delivered, morning, noon, and night. That one I had. Lions, tigers, and bears. Oh, shake, rattle, and roll. I would have never gotten that one. That's an old lyric from a movie, or a song, actually. Oh, there's another one. Oh, good gracious. I'll do another countdown. 5, 4, 3, 2, 1. Oh, bacon, less tomato. Planes, trains, and automobiles. Red, white, and blue. Shoot. Okay. Just last two notes on this one. Measuring current using an amp meter. How do you measure current? Well, you literally have to break the circuit and put an amp meter in series with the device. But you need to make sure that when you take this wire, there used to be a wire right here. When you take the wire out and put the amp meter here, you don't want it to change the current. And so a good amp meter has a resistance that's close to 0 ohms, so they don't actually affect the current. Where can you put an amp meter in the circuit below? You could break the wire there and put one in there. What would it have happened if you put an amp meter in here? It would still read that the current over here is still 1 amp. What would happen if you put an amp meter over here? Oh, by the way, amp meter, if you haven't figured out, the symbol for it is just a circle with an A in it. The current over here would have also been 1 amp. Why? Remember, the current doesn't change as it goes around the loop. You just lose potential. I don't know if we should do potential on this one. And then measuring voltmeter. Voltmeter measures the potential difference between 2 points. And so, for example, if you want to measure the potential difference of this battery in this circuit, you would hook up the voltmeter, which is a symbol is just a circle with a V in it, across those 2 points, and it measures the potential difference. So where would you want to put it in this circuit if you wanted to measure the potential difference across the two, or all these events here? If you want to measure the potential difference across this battery, you put it across it. If you want to measure the potential drop across this one, you just put it across that. And the same thing across here. And they're designed that their resistance approaches infinity. In reality, they can never quite do that. But you want to do here is you still want the current to go through this resistor. You don't want any to go through the voltmeter. So it's like it has an infinite resistance, infinity ohms. Ideally, in reality, they're never quite perfect. But notice again what's happening here. Assuming this is 0 volts, I'm up to 12 volts here. No change here because there's no resistance for an amp meter. Then here I'm still at 12 volts. Here I've got a 6 volt drop according to the voltmeter. I'm down at 6 volts. Still 6 volts here. This one says I've got another voltage drop of 6 volts, which means I'm back down to 0 volts here. And sure enough, it makes sense. I'm going to save household circuits for next time. With that, have a wonderful time with your homework problems. We are going to shorten this chapter down, I promise. And we'll talk to you soon. Bye.